This is the first of several lectures where we explore computing triple integrals in coordinates other than Cartesian coordinates. These are coordinates adapted to situations of special symmetry. Cylindrical symmetry is sometimes called axial symmetry, symmetry about an axis. Good example of an object with cylindrical symmetry is a cylinder. So what we're going to do in this lecture is we're going to understand how to describe regions with axial symmetry in XYZ space using cylindrical coordinates. And we're going to set up triple integrals as iterated integrals in cylindrical coordinates. Now I'll tell you a deep dark secret. We've already been doing this. All an integral in cylindrical coordinates is an inner integral over an axis, say the z-axis, and an outside double integral which is computed in polar coordinates. So some of the things you'll see today will actually look familiar from the previous two lectures. But we're going to systematically develop this idea of describing regions in cylindrical coordinates and setting up triple integrals in cylindrical coordinates. So let me first say what cylindrical coordinates are. Polar coordinates, r and theta, locate points in the xy plane, as you can see in the diagram here. All cylindrical coordinates do is add an extra ingredient, namely the z component. So that now allows me to move off the xy plane and to move up or down in z. So to convert between cylindrical and Cartesian coordinates is really easy, because you already know the polar coordinate piece. You know that to obtain the xy coordinates from polar coordinates, you use the triangle. So for polar coordinates, the triangle is your friend, right? The polar coordinate r is the hypotenuse of the right triangle. The polar coordinate theta is this angle. Y is the length of the opposite side, and x is the length of the adjacent side. And that's where these formulas come from. And there's no conversion to do on the z. Okay, and then of course I remind you that if you're given x and y, r is just the distance from the origin to that point, so this comes from the distance formula. And from trig, I see that the tangent of this angle is opposite over adjacent. That's where this formula comes from. Okay, so let's do some converting. I want to find the cylindrical coordinates of the point whose Cartesian coordinates are √3, 1, and 4. So the first thing I'm going to do is I'm going to compute what r is. So r squared is √3 squared plus 1 squared, which is 4. So that means that r is 2. Now what about theta? Well, I know that tangent of theta is 1 over √3. Since this point is in the first quadrant, right, x and y are both positive, that means that theta is pi over 6. The z is easy, that's z. So the coordinates of this point are, r is 2, theta is pi over 6, and z is 4. So those are the cylindrical coordinates of that same point. √3, 1, 4 in XYZ coordinates. Okay. So let's do another one of these. If you'd like, you might take a minute and try to pause the video and do it yourself. So let's find the cylindrical coordinates of this point. So first of all, r is equal to the square root of, let's see, x squared is 4. What about the y squared? That's 4 times 3 is 12. So that's √16 or 4. So r is 4. Now the tangent of theta is the y over x. That's 2√3 over minus 2. So that's minus √3. Now to deduce theta, I have to be a little bit careful. What I like to do is just out and out draw in the xy plane where this point lives. So x lives in -2, y is 2 root 3. So this point, -2 to root 3, is someplace over here. So that means the angle theta is somewhere between pi over 2 and pi. So we want to know what angle theta has tangent minus root 3. That's a large negative tangent. If you remember your tangents, you'll figure out that theta is 2 pi over 3. Okay, so we've got r, which is 4, and we've got theta, which is 2 pi over 3. So that means that the cylindrical coordinates r, theta, and z of this point are 4, that's the r, 2 pi over 3, that's the theta, and then the z coordinate is the same. Okay, now let's try to find the Cartesian coordinates of a point which is given in cylindrical coordinates. So x is going to be 5 times the cosine of pi over 4, which is 5 times root 2 over 2. Y is going to be 5 times the sine of pi over 4, which is the same thing actually, 5 times root 2 over 2. Z is z. It's kind of nice the way that works. So the Cartesian coordinates of this point are x, y, z equals 5 root 2 over 2, 5 root 2 over 2, and 2. Okay, the next thing I'd like to do is work on identifying equations and regions in cylindrical coordinates. The first task is to identify the polar curve r equals 2 sine theta. And let me remind you of a trick that you may have learned in a previous calculus course. So I want to remember that sine theta is the same thing as y over r. So I can rewrite this equation as y is equal to 2y over r. I can multiply both sides by r and I get r squared is equal to 2y. Now remember that r squared is x squared plus y squared. I can move the y to the left, complete the square by adding 1 to both sides, and I see what this figure is in Cartesian coordinates, or what this curve is in Cartesian coordinates, is a circle. It's a circle of radius 1 and center 0, 1. Okay, so here's a picture. The curve r equals 2 sine theta is a circle of radius 1 and center at the point 1, 0. Okay, so here's a puzzler. What would be the surface r equals sine 2 theta? So it's the same equation, but now we're talking about a surface. Now we're talking about cylindrical coordinates. So that means that the z coordinate is free to be anything it wants. So what do you think it is? If I were you, pause, take a minute, see if you can get the answer. Okay, so here's what the surface r equals 2 sine theta actually looks like. So you take this circle in the xy plane, allow the z coordinate to be either positive or negative, and what you get is a cylinder. So this equation is the equation of a cylinder. Here's another example of the equation of a surface in cylindrical coordinates. Here's the diagram. This is a quadric surface. How can I express this equation in cylindrical coordinates? Well, I need to remember that r squared is x squared plus y squared. So if I notice that the equation can be written 2 times the quantity x squared plus y squared minus z squared equals 4, then I can rewrite that in cylindrical coordinates as 2r squared minus z squared equals 4. That, of course, is a hyperboloid of one sheet. And there's its equation in cylindrical coordinates. Okay, so we've talked about equations in polar coordinates giving rise to curves and equations in cylindrical coordinates giving rise to surfaces. So here's checkpoint 1. I'd like you to sketch the solid described by these inequalities. Theta goes from 0 to pi over 2, and z runs from r to 2. So the theta going from 0 to pi over 2 singles out a region in the xy plane. But now what about r is less than or z less than or equal to 2? The way it will be fruitful to think about this is that there are two surfaces. Excuse me, let me write them this way. There's a surface z equals r and a surface z equals 2, which are going to form a bottom and a top. So think about what the surface z equals r looks like and what the surface z equals 2 looks like, and see if you can sketch the solid described in cylindrical coordinates by these inequalities. So here's the picture courtesy of computer graphics. Let's see if we can connect with the inequalities. So theta running from 0 to pi over 2 means that whatever the solid is, it lies entirely in the first quadrant. Excuse me, the first octant. What about the second set of inequalities? Z goes from r to 2. First of all, what is the surface r equals z? That's the surface where the radial coordinate equals z, so it starts out at 0, where r and z are both 0, and it moves diagonally upwards. So if you cut this surface z equals r with any plane, you're going to get a 45-degree line. Let me draw a somewhat less than beautiful sketch of just what that surface would look like if there were no constraint on theta. So the surface z equals r is this Dixie cup shaped region. So if you think about a Dixie cup, right? That's what z equals r is. So it says the distance you go out along in the xy plane is the same as the distance in z. So z equals r is a cone or a Dixie cup surface. What we've done with the plane z equals 2 is we've capped it off. So there's the plane z equals 2. That's the top surface. So using cylindrical coordinates, we can describe surfaces with some kind of axial symmetry. What this is, a way to think about this really, is take the poor Dixie cup and chop a quarter out of it. That's what the surface is. So now that we've learned how to describe regions and even solids in cylindrical coordinates, we'd like to use cylindrical coordinates to set up triple integrals. Let me remind you that in polar coordinates, the area element, if you like, is r times dr times d theta. So whenever we do a polar integral, it's an iterated integral over r and theta, but we have to insert this extra factor of r. Cylindrical coordinates work much the same way. The volume element has this extra factor of r because we're using polar coordinates plus a Cartesian z coordinate. And any integral we set up will go in the outside over theta, next over r, and then over z, but always with this extra factor of r. So suppose we have a region that we can describe in cylindrical coordinates. Well, first let's remember that the general form of a triple integral over a solid with a bottom and a top, so this is what we call type 1, looks like an inside integral over the z from bottom to top, and then an outside double integral. You may remember that in some of the triple integral examples we worked, that double integral could be polar. And this is what we're going to do now, is take the region D to be described in polar coordinates. That means that the whole region described this way, if D is in polar coordinates, and if Z runs from a surface given by a function u1 to a surface given by a function u2, we can convert this integral to an integral in cylindrical coordinates by doing the following things. First of all, we're going to express the integrand of function f in terms of cylindrical coordinates by substituting r cosine theta for x, r sine theta for y, and of course z for z. So I re-express this function using the cylindrical coordinate variables. Secondly, I describe the lower and the upper surfaces in cylindrical coordinates. I do that integral over z from bottom to top, but I wind up with a function of the polar coordinates. Then I do the outside polar integral over the region in the xy plane. So here's the rule for integrating over a region in cylindrical coordinates. And it describes a multi-step process. Let me go through those steps before we get into the actual calculations. So the first step is to express the limits of the inner integral in terms of polar coordinates. So find the limits of the inmost integral in polar coordinates. Secondly, substitute x equals r cosine theta, y equals r sine theta into the formula for f to rewrite f as a function of r theta and z. After making these substitutions, then, evaluate the triple integral. So let's see how this works. So in the inset up here, I've put our master formula for setting up a triple integral in cylindrical coordinates. Let's see how this works in actual practice. Suppose that E is a cylinder of height 5 and radius 3, centered about the z-axis with its base at z equals -2. Let's take apart that first statement. So it's a cylinder of height 5 and radius 3. So the radius from here to here is 3. The height is 5. If I start out with base at z equals -2, so that's below the xy plane. If I move up to a height 5, I go from z equals -2 to z equals 3. So that's a good picture of the cylinder. So what are the bottom and the top in this case? The bottom of this surface is z equals -2, and the top is z equals 3. Those are going to correspond to the lower and upper limits, so fortunately they're pretty easy to describe. Now what about the function x squared plus y squared plus z squared? Whoops. So x squared plus y squared plus z squared is just r squared plus z squared. Because of course, x squared plus y squared is just r squared, okay? So that allows me to re-express the integrand in cylindrical coordinates. So now I'm ready to set up the triple integral. I know that integrating over the cylinder, theta is going to go from 0 to 2 pi because I go all the way around the cylinder. The cylinder has radius 3, so for the r coordinate, I have to integrate from 0 to 3. And finally, we decided that the lower limits of the z integral are -2 and 3, and that the integrand is r squared plus z squared. And I know I'm supposed to integrate with an extra factor of r, integrate over z, then r, then theta. So let's carry out each one of those steps. Okay, so the integrand, let me just rewrite. Let's multiply through by the r so we don't get messed up with that. This is the same thing as r cubed plus z squared r, if I take into account the extra factor of r. Integrating dz is pretty easy. What I get is r cubed z plus, then what's the integral of z squared r? That's the r is a constant, and I get z cubed over 3. And I'm supposed to evaluate from z equals -2 to z equals 3. Take the resulting function of r and theta and carry out the triple integral. So when I do this evaluation, let's see, so r cubed z from z equals -2 to z equals 3 is going to give me 5r cubed. And then the r times z cubed over 3 is going to give me r times, let's see, what, 3 cubed over 3 is 9, minus r times -2 cubed over 3. So that's 8/3. Then dr d theta. Let me make some room up at the top here. So let me continue this calculation up top. So I'm supposed to integrate from 0 to 2 pi and from 0 to 3. The integrand is 5r cubed plus, let's see, 35/8 r dr d theta. Okay, the r antiderivative is not so bad. This is 5r to the 4th over 4 plus 35/16r squared. Evaluated from r equals 0 to r equals 3, then d theta. Okay. So when I integrate, I get no contribution from r equals 0. I'm going to get 5 times 3 to the 4th plus 35/16 times r squared, which is 9. When I integrate, this is now just a constant number. When I integrate over theta, I'm going to get 2 pi. So when the smoke clears and all the arithmetic is done, note to me, this is a restart on this example. So let's consider the following triple integral in cylindrical coordinates. The region is a cylinder of height 5 and radius 3, centered about the z-axis, with base at z equals -2. So here, below the xy plane is the base of the cylinder. That's supposed to be below the xy plane, where z equals -2, that's the yellow plane. If it's a cylinder of height 5, it goes from z -2 to z equals 3. And it's a cylinder of radius 3. So from here to here is 3 units. So how do I set up this as a triple integral in cylindrical coordinates? The projection of this cylinder is just a disk of radius 3. So theta goes from 0 to 2 pi. R goes from 0 to 3. The z values are easy. They go from -2 to 3. What we're supposed to integrate is this function re-expressed in cylindrical coordinates. We'll get to that in a minute. And r dz dr d theta. So to re-express this function in cylindrical coordinates, I simply notice that x squared plus y squared is the same as r squared. So that I can then rewrite the integrand as r squared plus z squared times r dz dr d theta. Always remembering this extra factor of r. So what I have to integrate over z is the function r squared. Let me just write it with the z, with the r multiplied in. So it's r cubed plus z squared r is what I have to integrate. Let's take the antiderivative of that function. That's the antiderivative of r cubed, z going from minus, let's see, so the antiderivative of r cubed is just r cubed z. And the antiderivative of z squared times r is r times z cubed over 3, integrated, or rather evaluated, from z equals minus 2 to z equals 3. Then integrated over r and theta. When I evaluate that antiderivative from z equals minus 2 to z equals 3, I get from z equals 3, that's going to give me let's stop and start over. In this antiderivative, there's an easy part and a slightly less easy part. The r cubed z is easy because r cubed is a constant. Z goes from minus 2 to 3. That's going to give me just 5r cubed from this first term. Then from the second term, I'll have to work a little bit harder because I have to evaluate z cubed over 3 from z equals minus 2 to z equals 3. So at z equals 3, I get 3 cubed over 3, or 9. At z equals minus 2, I get negative 2 cubed over 3, so that's 8/3. Integrated, whoops, there's no r, got rid of that. dr d theta. So again, where does this second term come from? When I evaluate this, that's what I get. Okay, so the upshot is I have the integral from 0 to 2 pi, the integral from 0 to 3, of 5r cubed plus 35/3 r, if I combine these together into a single expression. Integrated dr d theta. Let me take a minute to clear out some room so we can finish the calculation. So let's continue the calculation. Let's go from here up to here and take the antiderivative in r. The antiderivative of this expression in r is 5r to the 4th over 4 plus 35/6 r squared, evaluated from r equals 0 to r equals 3, and then integrated over theta. Let me notice that when I do this evaluation, and let me make this look a little bit nicer, that was 5r r to the fourth over 4. When we do this evaluation, we're just going to get a constant. So the integral over theta is just going to give us 2 pi. So let's just do that. And now let's evaluate from r equals 0 to r equals 3. I get 5 times 81 over 4 plus 35/6 times r squared, which is 9. That's going to be 2 pi. And then if you work out the fractions, the result is 6/15 over 4. So the final answer is 6/15 pi over 2. Okay, so that's the example of setting up and evaluating a triple integral in cylindrical coordinates in a very simple region where the cylindrical symmetry is pretty clear because it's, well, a cylinder. Okay, let's consider something similar, but with a little more going on. So the task is to find the triple integral of the function z over the volume that's described as follows. It's enclosed by the paraboloid z equals x squared plus y squared, and the plane z equals 4. And I've shown a picture over here. So the top region, or the top surface, excuse me, is z equals 4, and the bottom surface is z equals x squared plus y squared. So I need, first of all, to express these completely in cylindrical coordinates. So for the bottom, that's easy, because x squared plus y squared is r squared. The top, we're already there, z equals 4. The integrand z is fine. That's already in cylindrical coordinates. So let me set up the integral. What's the region? So I need to notice that this circle here, which is where the paraboloid and the plane intersect, has the following equation. So the paraboloid's equation is x squared plus y squared equals z. We're taking the intersection of z with z equals 4. So that intersection up here is a circle of radius 2. And that's the projection into the xy plane. Okay, so that enables me to set the polar coordinates as theta going from 0 to 2 pi and r going from 0 to 2. Then I'm supposed to integrate over z. That's from z equals r squared, the bottom, to z equals 4, the top. The function is z. And I'm supposed to integrate with the extra factor of r, first over z, then over r, and then over theta. So let's now calculate out that triple integral. It's the integral from 0 to 2 pi, the integral from 0 to 2. Now, if I integrate the function z times r dz, that's antiderivative is 1/2 z squared times r, evaluated between z equals r squared and z equals 4, then integrate the resulting function with respect to r and then with respect to theta. From the z equals 4 term, From the z equals 4, I'm going to get, let's see, this is 8r, right? Because z squared is 16, I take a half, that's 8. Then from the z equals r squared term, I get 1/2. Z is r squared, so z squared is r to the 4th times r is r to the 5th dr d theta. So now let's complete the job by finding the antiderivative in r and evaluating from 0 to 2 pi. Let me notice again that when I take the antiderivative in r, I'm going to get a number. So the integration over 0 to 2 pi is just going to give 2 pi times whatever that number is. Let's see, so I need to find the antiderivative. This is going to be 4r squared minus 1/12 r to the 6th, evaluated from r equals 0 to r equals 2, which then gives 2 pi times, let's see, at r equals 2, 4r squared is 16. R to the 6th is 64. The r equals 0 term gives no contribution. And when I simplify the fraction, I get 64 pi over 3. So here is a problem about setting up an integral in cylindrical coordinates that I'd like you to think about for a few minutes. So the problem is to set up but do not evaluate. The integral of the function x minus y over a solid E, which is depicted in this picture. It lies between two cylinders, namely x squared plus y squared equals 1 and x squared plus y squared equals 16. These are cylinders whose axis of symmetry is the z-axis. The solid is above the xy plane and below the plane z equals y plus 4, which is this plane shown here. So to help out, I've done the projection of this region onto the xy plane. So you should be able to set this up as an integral in cylindrical coordinates. Please take a few minutes and try to do that. Let's look at the integral in checkpoint 2. So first of all, let's figure out what the bottom and top surfaces are. We're told that the surface lies above the xy plane, so that makes the bottom surface z equals 0. We're also told that the surface lies below the plane z equals y minus 4. That makes the top surface z equals y plus 4. But remember that in order to do the integral in cylindrical coordinates, we've got to re-express this in terms of r and theta. Y is r sine theta. So the top surface is r sine theta plus 4. So what we've got now is the bottom and the top. What about the integrand? The integrand is x minus y. I need to express that in cylindrical coordinates also. So f of r cosine theta, r sine theta, and z is equal to x is r cosine theta, y is r sine theta. So that's my function f evaluated in cylindrical coordinates. Finally, what's the region of integration? Theta goes from 0 to 2 pi, since the projection onto the xy plane consists of the region between two circles. Those circles have radii 1 and 4 because the inner cylinder is a cylinder of radius 1 and the outer cylinder is a cylinder of radius 4. So now we have everything we need to set up the integral. On the outside, I have the integral over the polar coordinates, theta going from 0 to 2 pi, and r going from 1 to 4. Then I have the integral over z from the bottom to the top, so that's from 0 to r sine theta plus 4. The integrand is r times cosine theta minus sine theta, so I just factored out the r. Then I'm supposed to multiply by r, integrate first over z, then over r, and then over theta. So that's the triple integral for the function x minus y over the region that's described here. Okay, so now we come to checkpoint 3 with some hints. So I want to step you through deciphering the description of a region whose volume we want to take. It's a wedge-shaped region, we're told, and we'll work that out. We're integrating to find volume. So the function we're integrating is 1. That's easy. So we're told, first of all, that this region is contained in the cylinder x squared plus y squared equals 4. That's a cylinder whose axis of symmetry is the z-axis and which has radius 2. Secondly, we're told that the cylinder is bounded above by the plane z equals x. So I've drawn in here in yellow the plane z equals x. So whatever the top surface is what happens when you take a cylinder and you cut it at an angle with a plane. What my picture shows is just what happens when you cut the cylinder with the plane. And as you can see from the picture, when I cut the cylinder by the plane, what I get is an ellipse that's partly above the xy plane and partly below the xy plane. So what's this last condition going to do? So I took the cylinder, I lopped it off with this plane, but what does the last condition do? What the last condition does is it only preserves that region that lies above the xy plane. Let me go back, look at that picture. Can you imagine what happens if we take all this part out of the picture? What are we left with? We're left with this region that lies above the xy plane. And if I rotate the picture a little bit, it looks like this. So see if you can take a minute now that we've analyzed the region and deciphered this language, and see if you can write down the triple integral for the volume of this region. So let's see if we can now set up the integral. We need to work out the above and below surfaces. Remember, that's these ingredients in the integral. From the description we have, we know that the surface is bounded below by the xy plane, that's z equals 0. So that's going to give the bottom. It's bounded above by the plane z equals x, so that's the top. But remember that we have to express this in terms of cylindrical coordinates. X is r cosine theta. Okay, so that means we've now got the below and the above. The function is 1. So it remains to work out the limits. What's the projection of this region onto the xy plane? Well, if you look at where that projection is, so you can kind of see it here, right? It's going to be a half circle. But now that half circle, remember, the x-axis is here. So what's the range of thetas? That's going to be theta going from minus pi over 2 to pi over 2. And now this was contained in the cylinder x squared plus y squared equals 4, which is a cylinder of radius 2. So that means that the r coordinate ranges from 0 to 2. So what's the integral? On the outside, I integrate over the polar coordinates. Outside over theta, next one over r. Then finally, I integrate over the z from the bottom to the top. I'm integrating the function of 1. And so I integrate first over z, then over r, then over theta. And always remember this extra factor of r, because we're integrating in cylindrical coordinates. So that's checkpoint 3. Okay, so what happened here? First of all, we learned how to label points in x, y, z space using cylindrical coordinates. Cylindrical coordinates are really just polar coordinates with a z added on. We learned how to describe regions with axial symmetry using cylindrical coordinates. We learned that to integrate in cylindrical coordinates, you need this volume element. So the dv becomes dz dr d theta, with this factor of r coming from the fact that we use polar coordinates. And we learned how to set up triple integrals over regions with axial symmetry using cylindrical coordinates.